Okay guys, this video is going to go through lesson 3 of unit 3 in SL analysis year 1. We're talking about compound interest formula. Okay, so dealing with an application of an exponential function. Then we'll look at some examples, and we'll go into using that compound interest formula to come up with this, idea of what the number E really represents. So we've got 5 pages to go through, and let's get started. So, first thing to recognize is that this is the formula to calculate compound interest. Okay, so compound interest is a scenario in which the interest that you earn over the course of a time period is added to your balance, and then that original balance plus interest continues to earn interest. Okay, so that's why we call it compound interest, because at some point the interest begins earning interest on itself, and that process just continues and continues. Okay, here are the letters in the formula, and then what those represent. So this A is your final amount. P is the principal, which is the beginning amount, the initial deposit or whatever amount you start with. I, we're going to say, is the interest rate per compounding period. So that could be a yearly rate, it could be a monthly rate, it could be a quarterly rate, it could be a daily rate, but that's a key thing to distinguish, is that it's the interest rate per compounding period. Per compounding period. It's not always yearly. Okay? And then N is the number of compounding periods that you have. So if your time frame is 3 years and your compounding period is monthly, you're going to have 36 monthly periods over those 3 years. Okay? First example, we've got $7,000. We invest it for 6 years, and we get a quarterly rate, the interest is compounded quarterly, which means once a quarter, once every 3 months, at 5% per annum. Okay, and we want to figure out how much the investment is worth at the end. So A, this is our unknown. We don't know that. Our principal, our initial amount, is $7,000. Our interest rate per compounding period is 5% per year, but divided by 4, because that's a quarterly rate, so that becomes 0.0125. So it's getting 1.25% per quarter. Okay, and N, the number of quarters in 6 years, is 24. So if we want to do this calculation, we could say that the final amount is equal to 7,000 times 1 plus 0.0125 raised to the 24. Okay? I guess I'll go ahead and just do that calculation. So give me a second as I do that. 1.025. I'm going to raise that to the 24th power first, and then I'm going to multiply that by 7,000. So we get 12,661. Wow. So this is almost double. 12,661. I'm just going to leave it like that. Nearest whole dollar. Okay, second case. 2,500, 4 years, compounded semi-annually. This means twice a year. The interest received was $843.26. What's the annual rate of interest? Okay, so this is a little bit tricky, right? So our principal is 2,500. Okay, she received 843.26. So this plus her initial investment of 2,500 is what the final amount was. So if I take 2,500 and I add, all right, I'll take 2,500 and I add 843 to that, I'm getting 3343.26. So we'll put that in. So this final amount is 3343.26. Okay, 4 years is the amount of time semi-annually, twice a year. That means that there were 8 compounding periods, and I is our unknown. Okay, so I'm just going to put this equation into the calculator and use NSolve. Okay, really cool feature of the calculator. We don't have to, you know, isolate I. We can just put this in and use NSolve. So give me a second while I do that. Okay, so I want 3343.26 is equal to 2,500 times 1 plus, now instead of I, I'm going to put x in, and that's raised to the 8th power. Then I got to put my comma, put the variable I'm solving for, which in this case is x, and NSolve is telling me that I, my pen here, I is equal to 0.037. Okay, so the annual rate is equal to 3.7% times 2, because remember that 3.7 is a semi-annual rate, so that's 7.4%. Okay, so that's a pretty good annual rate. I would take that in a heartbeat. 7.5% a year. All right. Third question. We're investing $8,000, 6% per year, compounded monthly. How long will it take to the nearest month to double her investment? Okay, so she wants, let me go back to black. Go back to the same color I've been writing everything else in. So we've got 12,000, whoops, 16,000. That is 8,000 doubled. The principal is 8,000. The rate is 0.06 annually divided by 12, so that's 0.5% per month. And N is our unknown. So we want 16,000 to equal 8,000 times 1.005 to the n power. N equals, and again I'm going to use NSolve, but to make this a little bit easier, I'm just going to take both sides divide by 8,000, so I'm going to say 2 is equal to this using NSolve. I'm going to make my typing a little bit less. Okay, so I want my left side of my equation is just going to be 2, and that's going to equal 1.005 raised to some power x. And I hit the wrong button there, so sorry, you gotta bear with me. So, wow, this is going to be 138.98 months. How long will it take? Okay, so basically it's going to take 139 months, right? Because it doesn't happen on the 138th month, right? After 139 months, it'll be a little bit bigger than 16,000 because we know the exact answer is this. So it'll be that 139th month. All right, page 1 done. Now, as you can see, these are some more IB type questions. They're out of the textbook, I believe. And so we will go through these together. If you don't want to go through this part, you can skip ahead, all right, to when I'm going to page 3. All right. So we're going to do some different calculations here. I guess I'll do it over here. And I'll write out first what the computations are, and then we'll calculate. 1 year, 6% per annum. So the first part A will be 1,000 times 1.06. Part B, quarterly, that'll be 1,000 times 6% divided by 4 is 0.015, so we'll have 1.015. But now that's going to get raised to the fourth because you have 4 quarters to allow it to compound. Monthly, well, I is going to equal 0.06 divided by 12, which is 0.005. So we'll do 1,000 times 1.005 to the 12. Daily, we'll assume 365 days. Okay, so I is going to equal 0.06 divided by 365, which is yikes. And I'm just going to actually put that in. Okay, so this will be 1,000 times 1 plus 0.06 over 365 raised to the 365. Okay, so I'm just going to keep it, I'm going to keep this daily rate exact. Put it there. By the second, oh my gosh. So let me see. There are how many seconds in a day, and then we can multiply it by 365. So we have 1 day is equal to 24 hours, which is 24 times 60 minutes, which is 24 times 60 times 60 seconds. So that is equal to, let's see here, 24 times 60 times 60 is equal to 86,400 times 365. Well, I'm just going to leave it like this. So this is going to be 0.06 over 4,000 times 365. Holy cow. So our amount will be 1 plus that rate, 0.06 over 86,400 times 365 raised to the 86,400 times 365. Okay, millisecond. You know what, guys? It's just, I think over the top. I'm not going to do that one. Okay, so let's do these calculations, and I'll write in blue, right? And I'm going to erase all this. No, I'll keep it, but the answers will be in blue. So 1,000 times 1.06 is 1060. Quarterly. So now the 1.06 becomes 1.015 raised to the fourth, which is 1061.36. So this is 1061. 61. I was getting ahead of myself. 36. So a little bit bigger. Part C. I've got to do this. So now I'm going to take 1.005 raised to the 12th. And that's 1061.68, so still a little bit larger. 1061.68, so a little bit larger than quarterly. Daily. So daily now, I'm going to convert my 1 point something. I'm going to write it as the sum, so it's going to be 1 plus 0.06. 1 plus 0.06 over 365. And then I have to write my exponent as 365. That's 1061.83. So it gets even a little bit larger. Not by much, right? But it does get larger. By the second, well, now the 0.06 gets divided by 365 times, yikes, 86,400. And this exponent is 365 times 86,400. Okay, this one just becomes 1061.84. Okay, so if you look at these, right, we have 1060 to 1061. It's a $1.36 increase, 32 cents increase, 15 cents increase, 1 cent increase. So even though these values are going up, the increase each time is getting smaller and smaller. So we would think that, you know, this is going to be, you know, incrementally larger than 1061.84. Okay, so I'm going to say here that the values increase, but by less and less each time. Okay. Here we have a show that. So we want to convert this to this. Okay, and we can substitute that A is equal to N over R. So that means this is equal to 1 over A. Okay, so if we show that, this is equal to U sub 0 times 1 plus, now R over N is just 1 over A, right? So if I have A is N over R over N is equal to 1 over this, so it's 1 over A. And then NT, well, N is going to equal AR, right? Big N is going to equal AR. So this is raised to the ART, the art. And then if we really want to, you know, because these are all multiplied, we can change the parentheses. So I can put a parentheses around this, and it won't change anything. So this is the same thing as U sub 0, 1 plus 1 over A, right, raised to the A times the RT. And it's the exact same thing. And now this and this are the same. So the way this flows, right, is we go from here to here, here to here, and then that's the same as that. Okay, number 4. For continuous compound growth, the number of interest payments per year, N, gets very large. Explain why A gets very large as N gets very large. So what is this saying? Basically, if we shrink our timeline, right? So if we continue to pay interest all the time, the number of interest payments per year gets large, right? And that makes sense. Why does A get large as N gets very large? Well, because as N gets large, it's in the numerator of this. So if I increase the numerator value and R stays constant, A gets bigger. All right, so I'm not going to write that out, but if A is equal to N over R and the numerator continues to get bigger, the whole thing gets bigger. Copy and complete the table, giving your answers as accurately as technology permits. Okay, so I'm actually going to do this in Excel. And I wish I could show you guys that, but I can't really be good with Excel on my iPad. So you're just going to have to take my word for it. All right, so we've got A looks like it's 10, and then every time it's increasing by 10, right? Every one of these values we're multiplying by 10. So I'm just going to create a little formula in my cell and make the next cell equal the previous cell times 10. 10, 100, and I'm going to stop when I get to 10 million, which is, let's see, 1, 2, 3, 4, 5, 6, 7. So let's go 1, 2, 3, 4, 5, 6, 7. Okay, so I don't need these two. Don't need these. And what I'm going to compute is 1 plus 1 over that number raised to that number. Okay, so I'm going to create a second cell, and this is going to equal 1 plus 1 over this raised to this. All right. As accurately as technology permits. So let me make these a little bit more. Yeah, I think that's plenty. 2.593742. 2.593742. And now I'm going to copy that and paste that in these remaining 6 cells. Okay, next one, 2.704. Whoops. 2.704. 814. Next one, 2.716. 924. Next one, 2.718. 146. 2 more. Sorry, 3 more. 2.718. 268. 2.718. 268. All right. 2.718. 280. 2.718. 280. And then same thing, but 282. So we're seeing kind of this change in the values on the right side, the right column, get less and less, right? I mean, the change from here to here is probably the most dramatic. The change from here to here is 2, what is this? Tenths, hundreds, thousands, 10,000, 100, 2 million. So almost negligible. And then, basically it's, this limit, all right? So as A gets really big, as A becomes really big values, this expression is essentially equal to this, all right? So you can see we're really close. 2818, 282, right? So it's about the same. What do you notice? Well, if you compute E on the calculator, if you punch it in, it's that. It's this value. So you really could say that E is equal to, now we haven't used this limit notation. Oh, we have actually, I believe. The limit as x goes to infinity of 1 plus 1 over x to the x. Okay, so if you have this continuous growth where essentially the compounding period is instantaneously, right? It's, more than monthly, more than daily, more than by the second, more than by the millisecond. If it's always happening, there's a limit to what that will do growth-wise, okay? And the limit involves E. So if you see the words continuous growth or compounded continuously, that's financially, you'll see that. So I'm going to say compounded continuously in finance. Then your expression gets a little bit more simple. It's U sub n is equal to U0, e to the RT, okay? U0 is your initial amount, your principal. R is the annual percentage rate. T is the number of years. Okay, so they want us now to use the formula to find the value of 1,000 if it's invested for 4 years at a fixed rate of 6% compounded continuously. Okay, so more than every second, right? So I'm going to say that U sub 4, the amount after 4 years, is equal to U sub 0, well, that's 1,000, times E to the interest rate. The interest rate is 0.04, and the amount of time is 4 years. And I apologize, I thinking 4 too much. The interest rate is actually 6%, so this is times 0.06, or raised to the 0.06 times 4. I don't need that second parentheses. So this is the same thing as 1,000 E to the 0.24, and that's going to be, if you run on the calculator, which I'm going to do in a second, 1,000, holy cow, 1000 E.24 is 1271.25. 1271.25. All right. So we're going to stop the video there. But that's a good explanation, I think, unbiased, of these first 2 pages. Okay? So I will make another video going through the rest of these notes